So there should be 26 students.
Sure, I should start early.
So for those, who's taking 665? 664, I mean? Okay. So the nice thing about taking 665 and 664 together is that you're going to hear a lot of material more than once. And so you may get bored or whatever, but that will help. Because in general, 664 is a prerequisite for 665, but some people actually take 665 without taking 664. So I cover some of the important material from 664 in the first 2 lectures of 665. So if you have not, if you're not taking 664, so basically what I do now is I record the lecture and I post it online, just in case if you're missing anything, or because it's 3 hours. 3 hours is a long time, and you probably will fall asleep close to the end. And if you miss anything, everything will be posted online afterwards. To find any information, everything is available on eClass. So I'm going to go through eClass to show you what you have. First, you have the course outline. There's a lot of problems in this course that requires a lot of mathematical manipulations and a lot of solutions of equations. Now, I don't want you to use, you can use hand calculations, but sometimes the calculations are going to become large, and that's why I'm using Mathematica throughout the course. And here you have your options for using Mathematica. And I'm also going to, there are lots of tutorials on how to use Mathematica, and they are in your textbook as well. So, Mathematica tutorials, if you click here, you will find a few sets of lectures. These are tutorials that I posted for Mathematica, and it also includes how you actually can connect to use Mathematica. You will also find the lectures online under CivE 665, and also the 398 lectures and 664 lectures. So throughout the course, we might use, or I'm going to ask you by the end of the course to utilize the finite element analysis software. Now you're free to use whatever software you want. You can use answers, or you can write your own code. It's up to you, but I prefer that you use Abaqus simply because from a research point of view, Abaqus is, so far, I think, is the most powerful software. There are some tutorials. If you click on these, you will get those tutorials. And these tutorials were prepared a while ago, and I will go through them throughout the class as well. How to download and install Abaqus? There is a Microsoft Word here, a Microsoft Word document here, telling you how to download the software and install it on your machine. And when you download the software and install it on your machine, there's a lot of instructions just to make sure that you are one of our students, and you're not utilizing the software from outside the university. There's a lot of security stuff that you have to go through. So follow the instructions, and if you have any issues, let me know. The important thing about this is that when you download and install the software, you automatically have the student version. Now the student version is not that limited. It has a lot of nodes and it has a lot of elements. But if your supervisor, if you're doing an MSc or a PhD and your supervisor wants you to do research in Abaqus in the future, and if your supervisor is actually one of the contributors, because we pay a lot of money for this software, if your supervisor is one of the contributors to the software, and you want to utilize the full version, you have to just let me know, and I'll tell you how to convert the version that you have from the student version to the full version. but the full version is still, you can do anything in the student version. So in the student version, you can do anything that the full version can do. You have just a slight limitation on the number of nodes and the number of elements, but in the problems within this class, this limitation will not hinder you. The assignments, they're all already posted. We have 8 assignments this year. The blank lectures are lectures where basically what I will be saying, but with some blank areas, where you can, if you would like to write during the lecture, you're welcome to do so. Otherwise, you will find at the end of the lecture, I will post the lecture after I filled it up. In terms of the assignments, if you look at your calendar, I try to post everything on the calendar so that it's clear when everything is due. So your first assignment will be due Monday the 24th. So it's due Monday the 24th, and the assignments are due at the beginning of the lecture. So just bring it here. So those who have taken my courses before, I asked you to do a lot of work. So throughout the whole course, there's assignments, there's work, there's new material. I cover everything possible that's related to the finite element analysis method, and I also ask you to know how to do buckling and plasticity. And so there's a lot of stuff, but when I mark or grade at the end of the year, I consider that I'm actually asking you for a lot of stuff. I'm not just asking you for an introductory course where I just show you how to do how to just write the equations and invert a matrix. I'm actually taking you to more of an advanced finite element analysis course. So the course outline. So these are the topics that we're going to cover, and we'll talk about them as we go through the course. The grade distribution, the assignments are worth 25%. You have a midterm that's worth 25%, a final exam that's worth 30%, and a project that's worth 20%. And it's better if you're doing any research using finite element analysis, it's better that you do that project related to research, because you can get help at that time and you can kickstart your research using the software. Now the references, there's a course textbook available as an ebook through Civil Engineering Club, or Civil Engineering Student Society, or club, I'm not sure. If you have, the ebook has newer problems compared to the book that if you took 398 or bought the book itself, but I will be posting the new problems. So if you have the older version, or if you can buy the older version, it's fine. And if you don't want to buy the book, but you just want to look at the problems, I will also post the problems, so you don't have to buy the book. But I recommend it because it has a lot of reference material that you might need for other courses. At the end of the course, I will talk about nonlinearity, and for the nonlinearity I'm going to distribute some course notes because they're not in the book. Of course, you can use the Abaqus manuals. When you download the software, you're going to have the Abaqus manuals, and these are the tutorials. There are very nice books for your future reference. When I took, probably in my life, throughout my student life, I took probably 2 finite element analysis courses for credit, and I sat on 2 other finite element analysis courses, and I read many different books. And every book you read, you get a different point of view, and you learn something new, or you understand what you did not understand in the first book. So, the books that I recommend are here. And each book has its own advantages. And of course, in the future, if finite element analysis is the topic that you really like learning about, these are books that you should have. Here's a tentative schedule. Today we're going to cover linear algebra. If you're taking 664, this will be, again, just a review of what you should know from 664. And in the next lecture, we're going to cover stress, strain, and equilibrium equations and the closed form solutions. And then we're going to cover other topics afterwards. The first 2 lectures cover what we actually do in 665, but the important stuff that is required for this course. There will be a midterm, and I'm thinking that this year I will have the midterm as a take-home exam, simply because usually my midterms are really long. So a take-home exam, I will make sure that I will make it so that every student will have a different exam, so that, or different numbers, so that you don't have the option of copying from each other, but you actually have the option of sitting down and trying to understand what you actually are doing. And that will probably be the same for the final exam. I'll see the result from the midterm, and based on the midterm I will decide. At the end of the course, you have a project, and the project, the date of the project is usually, so for the project you have to give a presentation and a report. And I will post a report from last year. And you're graded on both the presentation and the report. So at the end of the term, you should be able to give a presentation on a finite element analysis topic. And you should be able to write a report on a finite element analysis problem. And so reports from last year's that were very good will be posted, so that you know what you should look for. Now, I grade on 2 things: your presentation style, how you write that report, is it complete, is it missing any information, and also the technical content of that report. So, I think if anyone here is my own graduate student, they've already heard this story before. In my own PhD defense, even though all my work has been finite element analysis, I was asked, what is finite element analysis? And my answer was not correct. Even though I had taken a few courses, and I've really done a lot of work using finite element analysis, but at that time, I still did not understand what I was doing. But hopefully, what I'm aiming for in this course is that if you get asked the same question, you actually know what it is. So, in general, finite element analysis is a numerical method. A A numerical method, let's understand what a numerical method is. So, a problem in front of you that says find x, that is phi is x squared equal to. And the analytical solution is that x is equal to, or an analytical solution, because it could be positive or negative root. But what you see here is that the solution is actually, I didn't really give you anything. Because I'm asking you, what's the number that when you multiply it by itself, you get 2? You tell me it's the number that when you multiply it by itself gives you 2. So you haven't really done anything. Or depending on, you're just telling me, yes, there is a solution, that solution exists within the real numbers, and I don't know what that, basically, I can't give you anything better than saying it's that wiggly sign over 2. However, I can approximate that solution using an integer. Sorry, not an integer, using a rational number. I can approximate. Root 2 with a number that I can handle or that I can work with. That is close enough to root 2. And hence comes a numerical method. A numerical method finds a numerical solution to a problem, and that numerical solution is close enough. Of course, we're not going to study that the solution actually exists. We're just going to assume, yes, a solution exists, and this solution might be something like root 2, and I'm trying to find an approximation to this solution. So there are different iterative methods to find an approximate solution to this problem. For example, the Newton-Raphson method, which we will study more in detail closer to the end of the course. For the Newton-Raphson method, you write an equation. You write f of x is equal to x squared minus 2. And you're trying to find what is x such that x squared minus 2. And then you use a Taylor approximation because you know that this function is continuous and smooth, which means any addition, if I add a small increment to x, this is equal to f of x plus partial f of x multiplied by delta x, which is h, plus other terms. And then any numerical method, and this is important, any numerical method to find a solution has to start with an assumption. I have to assume something. I have to start from somewhere. So here, I'm going to start by saying, okay, well maybe x is 1. So what happens when I put 1 here? 1 minus 2, I get negative 1, which is not really 0. Which means that x is equal to 1 is not acceptable. So then I would like to find h, which if I change that 1 with, I would like to find h such that this new function will be equal to 0. And this is f of 1 plus partial f and partial x multiplied by h. I would like to find this h, a change in 1, so that I get my solution to be equal to 0. I get my function to be equal to 0, and you get this h will be equal to half. So your new value is equal to 1.5. You try 1.5, you put it here instead of 1. I have a better approximation. 1.5 squared minus 2, you're getting closer to 0. 0.25. It's still not acceptable because it's really far from 0. So you do an iteration, you iterate this process, you find another h2. h2 is equal to negative 0.0833. Now x3 is equal to this. F of x3 is not equal to 0, but it's close. And so on. You keep doing this until you reach an accuracy that's acceptable to you. Now this accuracy will depend on what residual you have. Because you might have 0.007, you'll never get 0. For this particular problem, you'll never get 0. Because root 2 is not a rational number, and you're using rational numbers to approximate root 2. Because you're using rational numbers to approximate root 2, you'll never get 0. But you always get a number that's getting smaller and smaller and smaller. So as that number gets smaller, you have to decide what accuracy you're looking for, and that of course depends on your problem, depends on what x actually is. If x is a nanoscale, is something in the nanoscale, maybe you want the accuracy to be 7 multiplied by 10 power negative 10. If x is in the meters, maybe you want this residual to be in the millimeter scale. So it really depends on the value that you're actually trying to solve for. Now, what we presented is called an iterative solution, where you actually assume something and you get a solution. You check, is this solution good or not? Well, it's not very good. You iterate and you do it again. There's other solutions where you can use what is referred to as recursive methods. And recursive methods are methods in which you have a certain equation, the output from that equation, you use it again as an input to that same equation. And this is an ancient method that they used to find the square root of different numbers. So if you have x squared equal to 2, x is equal to 2 over x, x plus x is equal to x plus 2 over x, x is equal to x plus 2 over x over 2. Assume any value, put here the first value that you assumed, and find the new x. Well, after you find the new x, put it back here, and you find a new x. And so on and so forth, and you're going to find that as you do this, the new value approaches the value of root 2, again, because the solution is not a rational number, and I'm using rational numbers to approximate it. The difference, the x squared will never be equal to 2. It will be close enough, but will never be equal to 2. So the finite element analysis method is a numerical method that tries to find a solution to a certain problem. Now this problem is a differential equation that usually arises from Newton's equations of equilibrium. It's a differential equation of equilibrium that we will study at the end of next lecture. And usually the unknown is the displacement of the structure, and from that displacement I can find the strain, and from the strain I can find the stress, because I have a relationship between the displacement and the strain, because the strain is as we will study, the strain is the gradient of the displacement, and the stress is related to the strain using whatever constitutive law you're using. You're saying it's a linear elastic. If I know the strain, then I know the stress. If you're using hyperelastic or whatever, there's usually a one-to-one relationship for elastic materials between the stress and the strain. Knowing the strain, I can get the stress. Now, solving the Newton's equations of equilibrium, you can solve it in many ways. For beams, to solve Newton's equation of equilibrium for beams, we assume something, and we don't, which allows us not to use the finite element analysis method. And what we assume in beams is plane sections remain plane. So we assume a lot of restrictions for the beam. This allows us to actually solve the differential equations of equilibrium much easier. And we can find analytical solutions to beams, deflections, and stresses and strains within beams. And this, you will study analytical solutions in CivE 660, where you have the geometry is a beam, so we have a lot of control over the beam, but we have to put a lot of we have a lot of control over the geometry, but we have to put a lot of restrictions to be able to solve the differential equations of equilibrium that arise from Newton. In this course, we're doing a different technique. We're not constraining our geometry to beams, we're constraining our geometry to elements. We divide our structure into small elements, and we put restrictions on the deformation of such elements. And we try to find the best displacement of those small elements that would be an approximate solution to the differential equation of equilibrium. And again, I say that an approximate solution because my assumption is like a rational number, but my solution is like a real number. Because my assumption is very limited to what it can or cannot model. So in order to study 665, which is finite element analysis, you need to know what is the equation that we're actually trying to solve, what are the possible analytical solutions, and these are what we're going to cover in the first two lectures. And that's why we're going to first start with linear algebra, stresses, strains, and the beam approximation. Now, I would like to justify why I'm going to spend 3 hours with linear algebra, even though you probably studied linear algebra before. But linear algebra is actually, I consider linear algebra is the most important topic in any engineering discipline, because everything that we do in engineering depends on solution of equations. You have some equations that you solve them, you've got matrices, everything can be represented by vectors and matrices, and so you really need to understand linear algebra well. And there's a lot of things that if you're using a software gives you messages. These messages are rooted in linear algebra, and if you don't understand the linear algebra part, you don't really understand what the messages are. And I will start here with an example. Has anyone ever used any structural analysis or finite element analysis software? What does the software tell you when the structure is unstable? Yes? Negative eigenvalue, okay, so something negative eigenvalue. What else? Also zero eigenvalue. Or even the structure, or even a finite element analysis software like SAP will tell you the structure is unstable. It's flat out. So how can it be that smart to tell you that the structure is unstable? And it's in order to answer this question, I'm going to have to spend 3 hours talking about linear algebra, and at the end of today, you should know how the software knows that the structure is unstable just by manipulating matrices. So the solution is, how it knows, basically if the stiffness matrix, whatever the stiffness matrix is, which we'll study in the finite element analysis method, if the stiffness matrix is not invertible, structure is unstable. And the leap here, we have some mathematical argument. The mathematical argument leads us to a physical argument. So we need to understand what the mathematical argument means, and why does it lead to this physical argument that the structure is unstable. The stiffness matrix is not invertible is also equivalent to 0 eigenvalues. Negative eigenvalues just mean that the structure is softening. You have, and we will study this closer to the end of the course, the structure is softening means that if I'm applying P and I'm measuring the deformation of the structure, negative eigenvalues mean that the structure is softening. I'm increasing the deformation, but the pressure is, but the force that I'm actually applying is decreasing. That's what a negative eigenvalue means. So let's now start study linear algebra, and from the beginning to try and understand what all these things mean. So why study linear algebra in the first place? For different reasons. Reason one, because in finite element analysis I have objects in space, so I'm inputting objects in a three-dimensional vector space, so I need to know how I can represent all those points. All those points are represented by vectors. So I need to understand that space that I'm dealing with. And I also apply displacements, function of the position, and now I get a new displaced shape with new vectors. So I need to understand how to add vectors, subtract vectors, what's a displacement vector, and all that. Stress and strain and stiffness matrices, and relationship between stress and strain are all matrices. So we really need to understand what is a linear vector space with vectors and what are matrices. So a vector space is a set that is closed under addition and multiplication by scalar. So any of the following are linear vector spaces. R is a linear vector space because if I have 2 is a real number, 3 is a real number, if I add 2 plus 3, I end up with 5, which is another real number. Because I'm staying inside the box, I call this closed under addition. If I multiply any number by any real number, I get another real number, which means that when I multiply 2 real numbers, I still am inside the box, so that's why I say I'm closed or the set is closed under multiplication by a scalar. So R is not the only linear vector space. You also have R cross R, where R cross R is the set made out of two elements, one from the first and one from the second. So the set of ordered pairs. Any vector in the set, if you add it to another vector in the set, you get another vector in the set. Any vector in the set, if you multiply by any number, you're still inside that set. And so on. All of these elements, all of these vector spaces have the following properties. Every one of those vector spaces have a zero vector. So in R2, the zero vector is this vector. In R3, the zero vector is equal to this vector. Also, it has an inverse element of addition. If x is equal to the vector x1, x2, the negative x, which is what we call the opposite of x, is nothing but the opposite of x1, and the opposite over the inverse of x2. And when you add x and negative x, you get the zero vector, and so on. Not only this, also the space of matrices. The space of matrices, example, A is equal to 1, 2. The space of square matrices of size 3, if you add two matrices to each other, you get another matrix inside the same space. There is a zero matrix, which is the zero vector in the space, is made out of this. And negative A is the inverse element of addition of all these. So when we are working with finite element analysis, you are actually trying to solve, you have a huge matrix that's n by n. So that's why. So in finite element analysis, you have a matrix that's n by n multiplied by a vector that's n by 1, which is usually equal to a vector n by 1. So we need to, so we're working in a finite or n-dimensional vector space. So what does basis or the dimensions of the vector space mean? R is a one-dimensional vector space because everything in R can be written as a linear combination of one element, which is 1. Anything in R is written as a function of 1, or can be written as a function of 1.5 or 2. So you need one element in R to describe all the other elements in R. R2 is a 2-dimensional vector space because everything in R2 can be written as a linear combination of two elements. example of those two elements are I and j. They're not the only ones, but they're possible ones. But you've studied I and j in your linear algebra. And so on. R3, 3 elements. I, j, k. Space of 3 by 3 square matrices is a linear vector space. How many dimensions do you think that space has? Nine dimensions. So it's a 9-dimensional vector space because everything can be written as the sum of 9 elements, and these 9 elements are 1, 0, 0, 0, 0, 0. And so on. So everything in M3 can be written as the sum or in terms of 9 vectors. So we've defined what a vector space is. Throughout any numerical method, we need to measure something else other than adding vectors. What we need to measure is the displacement a good approximation or not? So for example, you have a structure. In this structure, you divide it into nodes and elements, and once you divide it into nodes, your unknown becomes the displacements of the nodes. So the unknowns are the displacements of those nodes. So this is an n-dimensional, I'm living in an n-dimensional vector space, and I'm trying to find a vector with n components. You do a certain iteration, and you find a vector. And then whatever measure you have, that measure tells you that this vector is not good enough. So you find a different vector. And when you find a different vector, how do you compare those two vectors? You have the first solution, and then the second solution. Let's call this V, or U and V. And so what we're trying to understand is how close U is to V. To know how close U is to V, we need a measure other than addition and multiplication by a scalar. We need a measure of the size of a vector. We need a measure of how the vectors are far from each other. And that's why we use, or most of the time we use Euclidean vector spaces, where in Euclidean vector spaces we utilize the Euclidean geometry. So in Euclidean vector space, we utilize Euclidean geometry. So the size of a vector in a Euclidean geometry, if x is equal to x1 all the way to xn, I live in an n-dimensional vector space. The size of the vector is measured using the geometric measure, which is x1 squared plus x2 squared plus x3 squared. Now this is called L2 norm. Because I'm squaring and then taking the square root. Now this is not the only way I can measure sizes. I can measure a size of the vector using what is called L1 norm. Because some finite element analysis softwares are going to tell you I'm using the L1 norm or the L infinity norm to measure how good of an approximation you have. Another norm would be norm x is equal to the absolute value of x1 plus the absolute value of x2 and so on. This is a legitimate measure of size of vectors. L infinity norm, norm x is equal to the maximum component of x. Take all the components of x, take the absolute value, find the maximum one of them, and that's a measure of your size. The nice thing about all those measures of sizes is that if the vector is actually the zero vector, the measure of size will give you 0. Any of those measures, if the vector is actually 0, if all those components are 0, any of those sizes will give you 0, which means it's a legitimate measure of size. Not only this, if the vector is not 0, then any of those measures will never give you 0. We measure the distance between vectors simply by subtracting the vectors and taking the mean. So this is the distance between vectors, the Euclidean norm of the difference. So distance between x and y is the Euclidean norm of the difference. We also need the direction, something to tell me about how vectors are far from each other. Am I going in the same? Are they in the same direction or not? And for this, I use the Euclidean dot product. X and y are elements of Rn. X dot y is defined as x1 y1 plus x2 y2 plus x3 y3 and so on. By definition, only in Euclidean vector spaces, norm x squared is equal to x dot x. Just because I'm using the Euclidean norm, the Euclidean norm is actually equal to the dot product of the vector. Since I defined the dot product, I'm able now to define orthogonal vectors. X and y are orthogonal, perpendicular to each other, if x dot y is equal to 0, so orthonormal basis sets. The change of basis is very important for, or it appears a lot in matrix manipulation. For example, which we'll cover again at the end of the lecture today, if you have any symmetric matrix, S11, S12, and this is S12, S22, and so on, so this is symmetric, because I'm using this because I'm using the certain basis set, so E1, let's say this is n by n, E1 is equal to 1 zeros, E2 is equal to 0, 1 zeros. If this is a symmetric matrix that appears in this n-dimensional vector space where I'm using this traditional basis set, I can find another basis set that's also orthonormal, in which this matrix is actually diagonal. Now, it would be much easier to solve if I can, instead of having a matrix that's full of numbers, if I can have a matrix that's full of zeros and only the diagonal has numbers. So how to move from here to here, and what's a basis set and what's an orthonormal basis set is important for us to understand how the finite element analysis actually works. So an orthonormal basis set is a basis set whose elements are both orthogonal to each other and have the size norm of 1. For example, in R2, E1 is equal to 1, 0, E2 is equal to 0, 1, E1 dot E2 using the Euclidean dot product is equal to 0, norm E1 is equal to norm E2 is equal to 1. Therefore, this is an orthonormal basis set. Or B prime, which is equal to E dash 1, E prime 2, E prime 1 is equal to 1 over root 2, 1 over root 2, E dash 2 is equal to negative 1 over root 2, 1 over root 2, which is basically this vector and this vector. They're perpendicular to each other. Any vector in R2 can be represented as a linear combination of those two vectors. Again, this is an orthonormal basis set. An example of a non-orthonormal basis set is this. Any vector here can be actually represented as a linear combination. Any vector in R2 can be represented as a linear combination of E1 and E2. And if you don't believe it, just put any vector. Let's put up the vector here. X equal to 0, 5. So 0, 5 is equal to alpha E1 plus beta E2. 0 is equal to alpha plus beta. 5 is equal to beta. Therefore, alpha is equal to negative 5. Which basically tells me that to represent 0, 5 using this non-orthonormal basis set, we need to walk. Because I'm using this direction and this direction as my basis set. You need to go negative 5 in this direction, and then positive 5 in this direction. And you're going to get this vector here. So any two vectors can actually be used as basis sets. Any two linearly independent vectors can be used as basis set. But orthonormal ones are easy to work with. And that's why instead of using 1, 0 and 1, 1, I'm using the traditional ones where when you take the dot product you get 0. The last thing that I'm going to talk about for this first part is the cross product in R3. The cross product is a very important operation that gives me a vector that's perpendicular to two other vectors. If I have a vector here and a vector here, that both are in R3, so this operation exists only in R3. If I have a vector u and v that are three-dimensional vectors, each has 3 components, I can give you a vector z z is equal to u cross v, such that this new vector z is perpendicular on u and v, which means z dot u is equal to z dot v is equal to 0. When you take a cross product of two vectors, you get another vector that's perpendicular to the original two. You also get, since I'm working in R3, I actually have 2 directions for that vector. I have z and I have negative z. To differentiate, I say that this operation is anti-symmetric. If I switch u and v, I get the opposite. I also utilize this operation for some physical measurements or for some physical quantities, and that's why I want to limit the size of that new vector to the area between u and v squared. So this area, I want the size of the vector z to give me this area. And to find this area, you will find that this is equal to norm u squared, norm v squared minus u dot v squared. So this is what the cross product does, and knowing this, you'll find that E1 cross E2 has to be equal to positive or negative E3, and so on. And we use the right hand rule for positive E1 cross E2. I choose the positive when the bases form a right hand rule, where this is E1, E2, and E3. When you take the cross product of two vectors, you already know the famous result, which is u2v3 minus u3v2 in the direction of e1 plus something in the direction of e2 plus something in the direction of e2. Now, I don't ask you to memorize anything. Everything, if the exam is not take-home exam, it's an open book exam. So I'm not asking you to memorize any of the equations. You just need to understand what you're doing. After the introduction of the cross product, I'm able to form something called a triple product of three vectors. Which tells me something about how this is u, and this is v, and this is w. Triple product gives me this volume. U dot v cross w is actually equal to v dot w cross u is actually equal to w dot u cross v. And for the proofs of all these arguments, you're going to find them in your textbook. And basically what we're saying is that u cross v gives you this area and this vector, which is perpendicular to both, which is basically the height of this object, so the perpendicular distance, and then taking that, so basically the area of the plug. So this is the area, and then you take the dot product between z and w, you get v volume. The nice thing about this, if u, v, and w are linearly dependent, which means they lie on the same plane, you're going to find that u dot v cross w equals to 0. And if u dot v cross w equal to 0, you'll find that u, v, and w are linearly dependent. So the triple product gives me a measure of whether these vectors are in the same plane or not. If they're in the same plane, I cannot use them as a basis for my vector space because they are a plane, they're not linearly independent. If they're linearly independent, and there are three, I can actually use them as a basis for my vector space. Notation. So throughout the course, if x is an Rn, I can present x like this, or I can present it like this. I do not differentiate between a row or a column vector unless I'm multiplying a matrix by a vector. When I multiply a matrix by a vector, I have to present the vector in a column vector. xi represents the component of x. The I component of X. And if M is a matrix in the space of the n by n matrices, then M has the form M11, M12, and so on. Mij is a real number representing the I or the component in the ith row and j column. So I'm going to give you a few minutes break. So it's right now 9:06. I'm going to start again at 9:11. 9:11 exactly.